We have a mesh, and we've set the physics at its edges. Now for the two files that decide how OpenFOAM actually solves, and this is where the finite volume method finally shows itself. Most tutorials tell you to copy these two files and never look inside. We're going to look inside, because between them, they control both the accuracy and the stability of everything you compute. First, the big picture. Solving a case is a pipeline, and these two files own two different stages of it. You start with the equations of fluid motion. You end with the velocity and pressure fields. In between, discretize the equations into a giant matrix, then solve that matrix. fvSchemes controls the discretization, how the calculus becomes arithmetic. fvSolution controls the solve, how that matrix gets cracked. Remember this split and neither file is scary. Open fvSchemes. It's organized by the type of derivative in the equations. Each block picks the numerical recipe for that derivative. ddtSchemes handles the time derivative. Euler for transient runs, or steady state when you only want the final answer. Grad schemes handles gradients. Gauss linear is the sensible default you'll use almost everywhere. divSchemes handles convection, the transport of momentum by the flow. This is the single most consequential choice in the file, so we'll give it its own moment. And laplacian schemes handles diffusion, the smoothing, viscous term. It also carries the correction for non-orthogonal meshes. Here's the choice that makes or breaks a simulation. For convection, how do you estimate a value at a cell face from the values at the cell centers? Linear interpolation is second-order accurate, it captures sharp gradients well. But it can overshoot, producing little wiggles that sometimes blow the simulation up. Upwind takes the value from the cell the flow is coming from. It's only first order, it smears sharp features, but it is rock-solid stable. It will not wiggle. So there's your engineering judgment. Start with upwind to get a stable, converging run, then switch to a more accurate scheme once things are healthy. Accuracy versus stability, you choose. Now fvSolution. Discretization handed us a huge matrix equation for each field. This file picks the algorithm that solves it. Each field gets its own entry. Pressure is the hard one, it usually needs a conjugate gradient solver like PCG, or the multigrid solver GAMG on big meshes. Velocity is easier and takes a lighter smoothSolver. The preconditioner is a helper that makes the matrix easier to solve, think of it as predigesting the problem. DIC pairs with PCG for pressure. You rarely change these defaults, you just need to recognize them. Two numbers in there decide when the solver stops, tolerance and relative tolerance. To understand them, you need one idea, the residual. The residual measures how badly the current guess fails to satisfy the equations. Big residual, bad guess. Each iteration the solver drives it down. Tolerance is the finish line. When the residual drops below it, the solver says good enough and stops. Ask for 1 times 10 to the power of -6 and you get a tight, accurate solve, but it costs iterations. RelTol lets it stop earlier each step by only reducing the residual by a factor, which speeds up the intermediate iterations in a transient run. Loose tolerance is fast but sloppy, tight is accurate but slow. That's a lot of settings. But as a beginner, only 2 really demand your judgment. Everything else, leave at the sensible defaults. 1. The div scheme. It trades accuracy against stability, and it's the first thing to change when a run won't converge. 2. The solver tolerance. It trades accuracy against speed. Master these 2 dials and you can steer almost any case. Look at our cavity again. Its scheme should now read like plain English. Euler in time, linear for convection, the cavity is smooth and well behaved, so it can afford the accurate scheme. Pressure solved with PCG and DIC, velocity with a smoothSolver. Every line is now a decision you understand. That's the engine room. fvSchemes turns the calculus into arithmetic, fvSolution solves the matrix that results. Know the upwind-versus-linear tradeoff and what tolerance means, and you're no longer copying these files blindly, you're driving them. Mesh, boundary conditions, schemes, solvers, everything is in place. Next episode we press run and watch it converge, reading residuals live, the Courant number, and how to keep a simulation stable while it's running. See you there. We have a mesh.